Hello, and welcome to this first week of this course on supervised learning. In this course, you'll learn about the core ideas and models from supervised learning. You'll learn about their motivation and theory, their implementation, benefits, and limitations. Supervised learning is far too large of an area for us to cover everything you might want to know in just 10 weeks of study. We've had to leave lots for you to explore for yourself as we go through this course, and going forward as you need more techniques once the course is over. In this first video, we're going to define what we mean by a supervised learning problem. We'll start off by considering what a learning problem is more generally, before then focusing in on what makes a supervised learning problem different from other types of learning. So what is a learning problem? Before we get started on defining what we mean in particular by a supervised learning problem, let's just back up a step and give ourselves some context to consider what a learning problem is more generally. A learning problem, or a learning task, is one that aims to describe the relationship between a set of inputs and a potential corresponding set of outputs. So, for an example without outputs, let's consider a child who can't read but is provided with these coloured alphabet building blocks. Even without the ability to read or write, the child will be able to group these into collections that are more similar and less similar to one another, whether that's based on font, colour or size, for example. To add outputs to this situation, we might additionally provide the child with a very patient teacher who associates each block with a particular letter for the child, A, B, C, D, and so on. The child learns the alphabet through exposure to many such examples, even though not every letter is identical. So, for example, we have 3 very different styles of the letter A here. From this language of inputs and outputs that I'm using, the more mathematically inclined among you might notice that the thing that we're trying to learn about in a learning problem is actually a function, a mapping from a set of inputs to a set of outputs. Let's go with convention and call this function f as we move forward through this video. So some related terms to supervised learning that you might have heard before are machine learning and statistical learning. Learning problems are very broadly defined and as such can be tackled by experts from a wide variety of fields. In this degree programme and in this course, we're going to largely focus on approaches arising from the fields of computer science and from statistics. Machine learning tries to solve learning problems by drawing on techniques from computer science, such as algorithmic design and optimization methods. Statistical learning, on the other hand, approaches the same problems by drawing on techniques from frequentist or Bayesian statistics. As one might expect, there's a great deal of overlap between these approaches to learning problems. Generally speaking, the distinction between the two is made based on the lens through which the problem is viewed. Machine learning puts greater focus on analysis and understanding of algorithms, while statistical learning puts greater focus on the analysis and understanding of the associated uncertainties. Both share the primary goal of efficiently learning about this mapping between inputs and outputs. It's just the approach that they take varies. Okay, so now that we have an idea of what a learning problem is in general, what extra is needed to make this into a supervised learning problem? And what do we call a learning problem that's not supervised? The distinction between machine and statistical learning was based on the approach taken to solve that learning problem. What defines supervised learning is a property of the problem itself as opposed to the solution method. In particular, the key feature of a supervised learning problem is that the learning is based on pairs of inputs and outputs. This is much like the idea of concept learning from psychology. Let's explore this idea with another example from childhood. A kid will learn colours based on a large number of objects that they've previously seen, which someone then associates with each particular colour: red, green, blue, orange, purple, so on. Assigning a colour label to each object in this way is often referred to as labelling the data. And as every very patient parent will tell you, that this is a very time-intensive process. Having access to these labels is the defining feature of a supervised learning problem. In this slide, we have another example in which our inputs are images and our outputs are numbers referring to the number of sides that the shape in the image has. Though we usually focus on the case where we have just a single output or target variable, we're not limited to just having one. we might be interested in 2 or more. The important thing is that we know the values of these outputs for each set of inputs in the data. So for example, we might also have a secondary output that indicates logically whether or not that shape is filled. We can also have a much larger set of inputs than just a single input, and thinking about a different representation of these shapes can give us an indication of that. So if we consider instead representing each pixel of every image by its RGB value, then what we have is for each image, our inputs are 3 vectors giving the red, green and blue values in each pixel. We now have 3 inputs and 2 outputs for each example, but we still have input-output pairs, so the whole problem stays within the realm of supervised learning. So if we view this mathematically, what we have is a collection of vectors, R1, G1, B1, the vectors of red, green and blue values in each pixel, and a function f mapping that to the outputs, which are a 1 to indicate that this is a circle, and a t to indicate that it is filled. We have one of these pairings for each example in our data. So now that we've introduced what a supervised learning problem is, what are some learning problems that aren't supervised? Well, rather than having output values for each set of inputs, we might only have inputs to learn from. This might be because the outputs we want to learn about haven't been decided on yet, they're very difficult to specify, or they're very costly to measure. In this case, we have no labels at all, and are close at the concept of pattern recognition from psychology. For example, we might have a large collection of objects and want to group them based on their similarity, or find the odd one out in a collection. We call these unsupervised learning problems, where we don't have the output corresponding to each input. You're going to learn a lot more about these in a dedicated course in the next term. There are also in-between cases, of course, which fall under the title of semi-supervised learning. In this case, we have labels or outputs for some, but not all, of the example inputs. Email spam filters are a good analogy here. You might flag some spam to your email provider, or some emails that they thought were spam, but really weren't. However, they're never going to know for sure whether the majority of your emails were spam or genuine mail. There are also related learning problems, known as online and reinforcement learning. These add additional structure to these sort of learning problems by having a dataset that continues to grow over time, or by giving you the option to take actions and gain feedback from the outcome of those actions. You don't need to know too much about these for now, but it's good to know that these fields exist. So when introducing a new abstract idea, it can be helpful to have a very solid example to ground your understanding of that topic. This is what I hope to provide with this image, showing you 3 potential learning problems, where we're trying to distinguish between cats and dogs. Can you identify which type of learning problem we have in each of these 3 cases? Go ahead, pause the video and have a think about it. Okay, could you work it out? So in the right-hand frame, we have a supervised learning problem. Every input image is associated with one output label, cat or dog. In the central image, we have an unsupervised problem, where no image has a label associated with it. And in the left-hand frame, we have a semi-supervised problem, where only some of our images have labels. So, finally, we want to give some motivation as to why we might want to learn about this function f in the first place. And there are literally thousands of reasons why we might want to learn about this mapping between inputs and outputs. There are as many reasons as there are applications of data science, really. Broadly speaking, though, these can be grouped into 2 general and complementary categories: prediction and understanding. We might want to predict the output y star for a new set of inputs, x star. For example, this might be considering to which year group a new student will be allocated, how likely that new student is to pass their exams, or how tall they might be. Answering these questions usually involves either interpolating or extrapolating in the space of inputs. we want to make an informed guess about what the output will be for a new set of inputs. If the new inputs are within the range of those that we've seen before, then this is called interpolation, and if it's beyond the range, then it's called extrapolation. Special care needs to be taken when predicting beyond the range of your observed data, because we can never really be sure that the same mapping holds in this new part of the input space. Rather than prediction, we may simply be curious about the map and F itself. This is often the case when data science and machine learning are applied in scientific context. We may want to consider questions like, how does age impact the chance of a stroke? How does fuel economy vary with vehicle weight? Or which characteristics most strongly define this species of flower? Again, we might be interested in the mapping F within the range of our observed data, or might try and understand this mapping beyond that range. So whether predicting or understanding, we can interpolate or extrapolate. Okay, so we've now introduced what supervised learning is, what it's not, and why we might actually want to go about doing it. We've met lots of new vocabulary already, but we'll expand this further in the next video, where we're going to solidify the concepts introduced here and create a minimal thesaurus of supervised learning terms. Thank you very much for your attention, and I'll see you in the next video.